In this section, I'll show you how we can obtain deflections for a deterministic structure. The assumption used in this section is the structure has to behave linear elastically. That is, their stress and strain has to follow a linear straight line, and also the deformations of the structure have to be very small. The objective of this section is to plot the deflection shape before and after the analysis, and you should be able to attain deflections at any locations of a deterministic structure. To draw deflection shapes, we start from support conditions. It's well known that the roller support, hinge support, they are reframed to move vertically but allowed to rotate, while the clamp support is reframed from both vertical displacement as well as rotation. Also, if you have two members connecting, depends on how they are connected. If they are fixed connected, in this case, this is a 90-degree fixed connected, then after deformations, the rotation angle for both components should be identical. On the other hand, if they are pin connected, after deformations, the rotations angle for both components could be different. Also, to draw deflection shape, we can use moment curvature equations, which is m over ei equal to curvature. And this is the sign conventions that we follow for shear force and bending moment, and this is a coordinate system that we adopt. Let me use a simply supported beam structure as an example and show you how you can draw the deflection shape. This beam is acted by two loadings. One loading is acting at the left quarter upward. The other loading is acting on the right quarter downward. So hinge and rolling support prevent both sides from vertical movement. And your intuition should tell you that the left side should be pushed upward while the right side should be pushed downward. So you could draw a deflection shape like this. So left side push upward while the right side push downward. So this is an indication that I have a concave curvature or negative bending moment. And this is an indication that I have a convex curvature or positive bending moment. So from negative bending moments to positive bending moment, so there must be somewhere in between one point that bending moment is equal to 0. So that point we call inflation point. So it's also a point that telling you that curvature should be equal to 0 because this is a negative curvature and this is a positive curvature. So if you do equilibrium analysis and draw bending moment diagrams, indeed you can confirm that the bending moment on the left side should be negative and on the right side should be positive, and there's one point in between that gives you 0 bending moment, which corresponding to the inflation point that you found from your draw. So you can confirm that inflation point from the bending moment diagrams, and you can also confirm that the deflection shape that you drew is correct. You can then go on to draw the bending moment on the tensile side. Next, I want to show you a few more examples to see how you can draw the deflection shape. First is a beam, roller support at the left and clamp support on the right. It's acted by a downward load of P. So your intuition should tell you that the reaction force at A should be upward and they should have an end moment at B clockwise. So if you do equilibrium calculations around regions of A, you should know that the bending moment should be this way. So that is indications that the curvature should be positive. Now, at the B end, because the bending moment is clockwise, so according to our sign convention, it's a negative moment. So you should see a negative curvature around B. So you have a positive curvature on the left and negative curvature on the right. So again, somewhere in between, there must be a point that the curvature is equal to 0, or the bending moment is equal to 0. So again, that is called inflation point. So a good deflection shape should be able to reflect both the first order information, which is the slope, as well as the second order information, which is the curvature. So including the informations of inflation point. Second example, I have a simply supported beam with two sides overhang, and I apply a moment at point A, clockwise. So I draw a possible deflection shape like this, and I circle these portions, indicating that this portion of deflection should be a straight line. I want you to think about it, why this portion of deflection is a straight line. The third example, I have a hinge support here, internal hinge, roller support, and at the end is a clamp support. There's a loading vertical downward P. So I can draw a possible deflection shape like this. This is a clamp end, so there's no displacement, no rotation angle. And then again, this is a roller support, no vertical displacement. Hinge support, no vertical displacement. I also highlighted this portion between A and B, and indicating that this deflections should be a straight line. Again, I want you to think about it, why deflections between A and B is a straight line. Quite often, if we want to draw deflection shape for two-dimensional structures, we assume that all members are actually inextensible, which means that the members cannot be elongated or contracted along the actual directions. So as a result, for instance, if we take a look at this single frame under horizontal force of P, because of the actually inextensible assumptions, the horizontal displacements of B has to be equal to horizontal displacement of C, because the BC component cannot be compressed or elongated. By the same token, if I have two bay frames like this under horizontal loading, then the horizontal displacement of B and C and D should be exactly identical. Also, because of this actually inextensible assumptions, all the points here, B, C, D, E, they are refrained from moving vertically because all the vertical columns are actually inextensible. So this is the actually inextensible assumptions that we adopt for two-dimensional structure. Now, there's another concept that we can use to simplify your calculations. It's called superpositions. So assuming that I have a structures but add on by two different loadings. One is a concentrate load, the other is distributed loads. So instead of doing this analysis using these two loadings, I can split the analysis into two cases. So I just do concentrate loading analysis and then distributed loading analysis, and then get the results, superimpose them, then I have the original loading conditions. So this concept is called superposition concept. Next, I want to show you three traditional methods to help you obtain the deflections of deterministic structures. These three methods are direct integrations, moment area methods, and conjugate beam method. First, direct integrations. Direct integrations is using Bernoulli-Euler equations that we have seen before. Basically, it's the moment curvature equations that we mentioned. d squared y over dx squared equal to m over ei. So y is the displacement, m is the bending moment, and ei is the bending rigidity of the structure. So mathematically, it's quite straightforward if you want to establish displacement from these equations. So all you need to do is to perform double integrations on m over ei. So then you will get displacement. Also know that the first order derivative dy dx is equal to rotation angle theta. So the moment curvature equation is d theta over dx equal to m over ei if you express dy over dx equal to theta. So based on that equations, if you want to set up the rotation angle, then it's quite straightforward. So all you need to do is to do one-time integrations of m over ei. Then you get rotation angle. So of course, the integrations needs to couple with the boundary conditions. So with the proper boundary conditions, then you can obtain displacement and rotation angle for the structures. I'm going to use this structure to illustrate how we can use the two equations to obtain displacement and rotations of this structure. So this is hinge support, roller support, roller support, and roller support, and inside there are two internal hinges at B and E. The structure is loaded by distributed loads of 5 kilonewton per meter between A and C, and 3 kilonewton per meter between C and F. Notice that this is a deterministic structure. There are a total of 5 reaction forces, 1 vertical, 2 horizontal, and then vertical, vertical, vertical. So there are 3 equilibrium equations you can use, plus there are 2 internal hinges you can use to solve this structure. So equilibrium can help you to solve the structures. Assuming that you obtained the reaction force, and you can go ahead plot the shear force and bending moment diagrams. So notice that there's a positive regions and negative regions for the bending moments. So these bending moment expressions, if you can formulate them, then you can put them into the two expressions and obtain the rotation angle and displacement respectively. Of course, you need to pay attention to the boundary conditions. Also, with the bending moment diagrams, it can help to construct deflection shape. So the positive bending moments should corresponding to positive curvatures or convex. And negative bending moment should corresponding to concave curvature. And at the right side is a positive. So again, convex. And complies to the support or boundary conditions, then you can draw this possible deflection shapes, which tells you that this is convex, this is convex, concave, and this is convex.